Morning everyone. Before I start my thing today, please make sure that you have the file that you see on the screen right now in all of your PCs. You'll be needing this file to start modeling in Perform 3D. So please raise your hand if somebody doesn't have this file, and maybe one of my colleagues will come and assist you. They'll give you a copy of the file. You should have it. Actually, it will be easier if we email it to you right now, but maybe the internet is not available. So before I start, just to make sure, and I'll not start before everybody has this file, right? Okay. So let me just start with okay. So yeah. So. Okay, what is the file that I have shown on the screen right now? The general procedure of starting modeling in Perform 3D is that you can draw the nodes and then draw the elements, but we have to be a bit clever. Normally, when you are making a nonlinear model, before you start making a nonlinear model, you should already have a linear elastic model. And since you've already made a linear elastic model in ETABS, you can get the geometry file from ETABS and just import it in Perform 3D. So no need for you to start making the geometry again and again. If we start to make the geometry in Perform, then it will be very, very tedious. So the easiest way of doing it is that we will just import the geometry. And the file that you see on the screen right now is the file that is generated by ETABS. Now, a word of warning over here, this file will only be generated by ETABS 9, ETABS version 9. So you might not have this file in ETABS version 13 or 15. If you have version 13 or 15, there are other ways of importing the geometry from ETABS to Perform, but this file is generated by ETABS version 9. Now, if you are wondering how we get this file from the ETABS, the handouts that you've been given today will already show you how to get that file from ETABS. So, because I do not have ETABS 9.7 available with me right now, I cannot show you how to get this file from ETABS. But the handout that you have for the presentation today will show you how to get the file. It should be very, very easy. I think you just have to pick few options and you get this file. So, okay. I'm just waiting right now to make sure that everybody has the file so that I can start. Okay. If you do not have a handout, the handout that you were given yesterday, in that one, the presentation on Mr. Ong's name is the same handout that you were supposed to be given today. So you can use that one also if you want to use. The review of overall tall building response to ETABS model, actually that should be, the topic is not correct in that one. So maybe you can use that one. If everybody has the file that they were given yesterday. Okay. So, and I'm assuming that all of you have the file with you already, right? Yeah. Okay. Okay, so let us start. I'll start with the hands-on training today. Okay, and if I'm going a bit too fast and you are confused with something, you can just raise your hand and one of my colleagues will come and assist you, because sometimes it's a bit difficult to control the pace because we have to cover a lot of things. So please feel free to just raise your hand if you are not clear about anything. I will not be stopping, but maybe one of my colleagues will come and help you with whatever you need, right? So, okay. So let me just start. I'll start by opening this file. The file, you can open this file in a notepad. So, alright. Okay. So the file that you see over here is just a file that is generated by ETABS. Now this file has a lot of numbers over here. The first row is actually just representing a line element from ETABS, right? The first three numbers are the X, Y, and Z coordinates of the I node, and then the last three numbers are the X, Y, Z coordinates for the J node. So Perform 3 basically needs this data, and then if you give it this data, then it will use this data to make two nodes, one at the I end and one at the J end, and then it will draw the element for you also. So let me just copy the data in Excel. Okay. And then this is just a comma separated file, so you can just use this option. Text to columns, and the data is delimited by comma. Okay, so we already have this file in Excel. No need for us to copy or paste this file in Excel right now. Actually, you can directly use the file that you have to import and perform, but I just want to explain one or two things over here, so that's why I copied in Excel. There is no need to copy in Excel also. This is just for your explanation. So this is, let me just add one row. So this is, okay, this is the I node, and then this is the J node. And then this is the X, Y, and Z coordinate of the I node, and then X, Y, and Z coordinate of the J node. Now this data over here is for line elements. So you only need two nodes for line elements. If I go down, you will see that then you will start to have a bit more data in your row. This is because now this data is for area elements. So area elements generally has 4 nodes, and then you get the 3 coordinates for each node, so you have 12 node data over here. The important thing just to remember here is that this number over here, because when we start to import, we will just need this number to know how many lines to skip. I'll show you how to do it. And let me just make sure. Okay. So I'll start Perform 3D, and then maybe okay. So let's begin the modeling. Okay, sorry. We'll start with a new structure. So I'll just call it test structure. We have to take care with the units. Please note that the units in the file given to you are in kilonewton and meter. So we have to make sure that these units are in kilonewton and meter also. You can change them at the time that you are importing, but just to be consistent, I'll keep the units here in kilonewton and meter. Right? You can give some description also if you want. Anything is fine. This option over here just needs a little bit of explanation. Very easy. This is the minimum spacing between the nodes. So if you have nodes that you want to be close to each other, you should specify the minimum spacing to be as low as the program permits. So if it is permitting as low as 0.05, we just select this point, right? Just select this option, and then we're done. You can select a user-defined location also if you want for your program where it will be saved, but okay, I'll just use the default location for now. Yes, okay. Okay, so just some general thing about the program. There are normally 2 phases in this program. There is a modeling phase. You can see over here when I put my pointer at this location, it shows you the modeling phase, and modeling phase has all of these options shown over here. I'll be discussing most of them throughout the day. And then you have an analysis phase. Analysis phase is basically everything that is related to the analysis. So you can see that the options over here will change if I select this option. But let us focus on the modeling phase right now. Right. So the first option that I will be discussing today is the option of elements. This is the place where we will start making our groups. Now, as I mentioned to you before, yesterday, that Perform 3D you have to make groups for different types of elements. So let me make a group. Okay, one word of information over here. The file that you see in this location actually contains the data for line elements, but the line elements can be beams or columns. Right now we have not separated them. If you want, you can separate them in an Excel file, but I'll show you how to separate them in Perform. Right, so there are many types of elements that you can select. You can select a bar type element. If you select a bar type element, the properties that you can assign will be for a bar type element also, just uniaxial element. You have a beam type element, column type element, and brace other frames, panel zones, and many options over here. But let me start with simple brace or other frame option. I just selected this option because the group that I'm using to import the properties has both beams and columns. And then later on I'll just show you how to separate them. So I'll just write the name frame for this group. Right? So I have already created a group. Now the elements can be imported into this group. Right? Without this group, you cannot import the elements. So you need to make the group. Should be simple. And I'll also make a group for all of the beams. Right? And then because later on we have to move the elements to the beams. And then a group, which is the group type is column, and then I'll make a group of columns also. Okay. Right. So we already have all of the groups. Now we just need to start importing the data. Right. The import and export option in Perform 3D is shown in here. This option that I am highlighting right now is the import and export data option. Right? We just click this option. You can see that the program is allowing you to import and export a few things. Not everything can be imported and exported, but okay, some things are allowed. So I'll just be using the import option because we are importing the data from the file that I already showed you, generated by ETABS. Now the option that I'm using here is the frames option, right? And all I need to do now is just give the, okay, I need to see where the file is. I also don't know what's happening. Okay, so you can okay, my desktop. Okay, so if it is, I just did this a bit quickly. Maybe you will need a bit of time to choose the location of the file. Okay, so better that you guys choose it, because if you are stuck here, then we cannot proceed further. So if you have any problem while selecting the location of your file, maybe I'll give you a bit of time to select the location of the file. Right? Okay. So if you see the file over here, the data in this file doesn't begin from the first line. The first two lines, there is some text written over it, and then the third line has nothing in it. So when we import, we will skip 3 lines. Only that. And then we will ask it to read everything in that file. Now what happens is that the program will start to read the files from the 4th line. It will skip first 3 lines, and it will continue to read until it reaches an empty line. So as soon as it reaches the empty line, it stops reading. So the empty line is located over here. That is why the file generated by ETABS has a separator between the area elements and the line elements. Because you cannot import area elements, or you cannot import area elements into a line element group. Right? So just that. And Okay, so I'll skip 3 lines and we will not be including the orientation data because you see that the file over here has only coordinate data. There is nothing mentioned about the orientation in here. So I'll not check this file and I'll test it, and then you will see that all of the elements from E-tabs for our sample model have been imported. Right? So I'll just stop over here, and then maybe if anybody has any problem in importing this file over here, do raise your hand so that somebody can come up and help you. So all of the area elements are already imported over here, right? So now I will move on, and then I will show you how to separate the groups between columns and beams. So when I import it with a group like this, right? If the group is like this, you can see that beams and columns are in one group. But generally we would want to separate them into 2 different groups so that we can only work with beams and columns separately. So if you want to change the group, the option that you can use here is the change group option. Right? And then if I use the change group option, I will ask the elements to be moved to beam group. This is the beam group, it will move it. You just simply need to drag it over here like this. All of the elements behind it are also selected. So you can go to the H1 or H2 view, whichever you find easy, and start selecting the elements like this. Okay, if you do like this, then press the move button. Okay, all of the elements have moved into your, yeah.
How many lines to skip? I think something.
Okay, you can see the number over here.
But this is your file in Excel. Your text file is different.
It's at one.
You insert a few lines.
Okay. If it is like this, then maybe, okay, sorry. So sorry about that. Maybe I inserted one more line over here, so you can skip maybe one more line. So, one less line.
2 lines, or I think it's 2 lines.
No, I think there's generally 3 lines that are already skipped, and then I added one more. So if it is 3845, you can skip 3844. I think.
4. And do you need to read the notes as well as element?
I'm sorry.
Do you need to choose the option read notes as well as elements?
Yes. Normally that should be the option that you should be selecting.
3844.
Okay.
Yeah. No. I still have the error.
What error do you get?
One or more elements is not properly shaped.
Okay. If it is the error like that, you can select the other option. Here, this option.
Which option?
I'm sorry. I'll explain it over here.
Okay.
If it is unclear when you are importing, you can try with 1 or 2 options. Now, there are 2 options of the node sequence. Generally, we do not know what is the node sequence. So you can either select this option or this option. Play with the options and then try to import. You can import them. Right? Okay. Okay, so let me move a bit further now. I think it will be very, very difficult if I stop at every point. I will not be able to finish anything today. We will be stuck at the geometry. So I will move on, and maybe if you have any queries, you can ask one of my colleagues. They will help you in any issue that you are getting over there. And then I'll move further ahead, and if you are not able to do something, you can stop it, you can follow me what I'm doing, and then later on you can see the handout, because the handout should be very, very clear also. It is quite clear. Yeah, so now what I did last time was I was moving the beams into their proper group. So I used the change group option. This is another way you can do it. You can do it from plan view also. You use the change group option. This is the frame group in which I imported beams and columns. I'll just drag over the beams in the in this area, and then okay, so just drag over the beams and then you just move them. The group that they will be moving to will be the beams group, so you just move them over there, right? And then if you want to move the columns, okay, there are some beams left, so I'll just select them over here and then move them also. So everything from the beams group has been, from the frame group has been moved to beams. Now if you want to move the columns, the only remaining thing in this group is the columns. You just select the columns option, you drag over the entire thing, all the columns you can see that are already selected, and then I'll just move it to columns group. Now if you see, the frames group has no element. If it has any element, there will be something blue shown over here. So now I have already moved everything from the frame group to the beams and columns group. Now if I select the beam group, okay, so you can see that if I select the beams group, everything, all of the beams are in this group. Now if I want to assign the properties, I can assign the properties to the beams in this group. If I want to assign the orientations and everything, I'll be discussing all of the things over here, we can assign it. Now no columns are available in this group. So that means that when we assign the properties, all of the things that we will be assigning will be related to beams. Nothing will be related to columns. So easy to work with. That's why we separate them in the groups. So you have columns group also. That you want to work with the columns, then you can work with the columns over here, right? So only that. And then you have a shear walls group. Now if you want to move the shear wall, or okay, you can make another group over here. The group will be called slabs, and then the group type will be slab or shear, right? And then just press OK. So from the shear wall group, you can then start to move your elements into, or your slab elements into your shear wall, into your slab elements group. Now if you see, this shear wall is the area type group. If I want to move it into some other group, I can only move it to slabs group. I cannot move it to frame element groups. That the program will not allow. So if I want to move the slabs from the shear wall group to the slab group, I just simply drag over them, avoiding the shear walls, of course. And then, okay. If I drag them in the plan view like this, you can see that they are selected throughout the structure. So whatever, if you drag, whatever is below that thing will be selected, right? And then you just simply press move. So we are done. So now the shear walls are in the shear wall group. The slabs are in their own group. The beams are in their own group, and the columns are in their own group, right? And then the frame element group that I define has nothing in it, so I can just simply delete it. No need for you to delete, but if you want to delete, you can use this option, right? So this is all about importing the geometry from ETABS to perform. So as you can see, what I did was that I just simply used the text file that was available, and then using that X file, I imported all of my geometry from the ETABS model to Perform model. So it becomes very easy, because if you have to make this thing in Perform by yourself, will be a bit tedious, because you have to draw the nodes, draw the grids, and then draw the elements by yourself also. So it becomes very tedious, and then you should already have ETABS or linear elastic model from ETABS available for you to get the geometry from, right? Now, since all of the importing has done, I am not sure how many of you have been successful in importing everything. I think if you have some issues with importing anything, you can ask someone to help you, or you can also read the handout. The handout should be pretty clear as to how to import this geometry, right? So this should be it basically related to geometry, right? So after we have define the geometry in Perform 3D. Okay, let me do like this. Let me pause for 5 minutes, and then you guys can see if you have been successful enough, or you can ask someone to help you.
Not like that. Okay, yeah. You don't select the
When you have already defined the properties of a cross section, sometimes we want to use the stiffness modifiers, right? So we want to modify the bending stiffness, or we want to modify the axial stiffness, or whatever stiffness that we want to modify. We just need to change the numbers that are being automatically calculated by the program. So say for example, in a beam, generally the stiffness modifier that we will modify will be related to I3, the bending inertia about axis 3. So if I want to modify this one, what I can do is that I can just copy this number, right, paste it in Excel, and then use the modifier. So if you follow ASCE 41, the modifier, the bending modifier for a beam is 0.35. So you multiply this number with 0.35. Right? You get a new number. You copy this number and then you paste it here back again. Right? And then you just check and save. Done. So this is the way that you will generally use your stiffness modifier in all of the cross sections. So any property that you feel like you want to modify, you can modify it like that. You can ask the program to use the rectangular option if you have a rectangular section. It will calculate all the stiffness section properties for you. And say for example, if you want to use some modifier in some bending or some axial stiffness, you can just copy the number, multiply it with that number, and then paste it back again. So the stiffness modifier is already done. Right? And because there is no global option like in ETABS, you can select all of the elements and assign one stiffness modifier. Here it is not like that. Here the stiffness modifier will generally be assigned to a cross section. Right? Now what we have to remember is that this is simply just one cross section. This can be the property of a beam also, and the beam can have more things than a simple cross section also, like an inch or something like that, right? So that one should be. I will show you how to assemble a complete beam cross section or a complete beam compound, whereby you add all of the elastic properties like a cross section, and you also add all of the nonlinear properties like a hinge, and you add the stiff end zones, everything, and then you can assign that property to a beam. But this is just simple cross section definition. Now what I will do is that I will repeat the same process for a column cross section. should be exactly the same, just that the option will be different. So you can follow. If you want to follow right now of defining the cross section, you can follow defining a beam cross section or a column cross section, and then the process is exactly the same. So you just go to the column rectangular section option over here, right? And then you repeat the process. That's it. The same thing. I'll do it again, just so that you guys can follow. If you want to define a beam cross section or if you want to define a column cross section, you can define. No need to define both of them. We cannot make a complete model here today. This is just some simple demonstration. So I can only show you how to define a beam or a column cross section. We cannot model the entire structure today. Right? So I will repeat it, and maybe you guys, if you want to follow, you can follow defining a cross section like I'm doing. Right? So I'll define a new cross section for column. I'll write the name. Now I'll just simply copy the numbers that are shown in the handout so that it becomes a bit easier. 800 by 1400. So this is the 800 by 1400 cross section. Right? And then I will just select the rectangular shape. So because my units are in meter, so I'll just simply write 0.8 for my width and 1.4 for my depth. Now if you can see in the cross section, the depth is always along axis 2. So you have to remember that when we assign the orientation to a compound or to an element, you have to remember that the depth shown in the cross section over here is always along axis 2. Because when you assign the local axis, you will assign the local axis according to axis 2. So the depth is along that. And then you ask it to calculate, right? And then you can just use some stiffness modifier, some modulus of elasticity. This one, the number I'm copying from the handout, right? And then check and then save. Now this cross section over here does not have any stiffness modifier right now. Now if I want to modify the stiffness, what I will do is that I will copy this one, copy the number, and then paste it in Excel, or you can just use your calculator also. You do not have to copy and paste it in Excel. If you are comfortable with something else, you can do something else like that. Normally the stiffness modifier for a column is 0.7. You can refer to the guidelines that I talked about yesterday, and then you can see the stiffness modifier numbers. Right? So I already have the modified stiffness. So this one was the initial bending, and then I already have a modified bending inertia, and then I just paste it over here. In column, generally we will modify the bending for both axes because column is biaxial. So just simply paste the other bending inertia over here, and then multiply this one with 0.7. Very easy to do, and then copy it, and then paste it. Okay, so done. So I think this should be very, very simple. Defining a cross section over here for a column and a beam. Now this is just simply a simple cross section. And when you want to assign the cross section to an element, you have to compound it first. So you have to put together all of the things. I'll explain this one through the picture that I showed yesterday in my presentation. Should be okay. This one, just a bit of explanation. Okay. So if you see over here, generally when we assign a property to a beam in perform 3D, for the beam that we want to be nonlinear, we will need three main things. So we will need an elastic section or elastic segment, right? Now the cross section that I already defined right now is the elastic segment shown in here. But we've not put it together in a form like this. We will do it. We will do it later, right? And then what we need is that we need to define hinges over here, right? And then we also need a end zone, a stiff end zone. Now why we need the stiff end zone, I already explained it yesterday. So we need these three things and then we can put them together, and then we can assign this entire assembly to an element. Right? So since I've already shown you how to define a cross section, I'll move further ahead, and then just maybe I will copy the data that we have in the handout to show you how to define a hinge. So I'll just simply copy the data for you to define a hinge. Right? Now if you want to define a hinge, you can go to the inelastic tab over here. So the cross sections were here, right? And then if you want to define a hinge, most of the hinges or nonlinear properties are here in this tab, the inelastic tab, right? So you can go to the inelastic tab, and then just basically select the different types of hinges available. Now if you see the options of hinges available to you for beams and columns and axial elements and panel zones and dampers and everything, there are a bit too many options for us to cover over here. So the very basic option that I will cover here today is the option of the moment hinge rotation type. Now, what do we mean by moment hinge rotation type? Basically, I'm talking about this option over here, moment hinge rotation type. What do we mean by moment hinge rotation type? The moment hinge rotation type is basically the hinge in which the force deformation relationship is between moment and rotation, right? So, you need to have the moment capacities and the rotation capacities of a beam before you will be able to define this property over here. Now, it will be very tricky for me if I went into the details of how to calculate the moments and how to calculate the rotations and everything. But what I can tell you is that you can use simple mechanics to calculate the moments, right? You can follow the guidelines that were shown to you yesterday. I showed you many, I think around 4 guidelines. Most of them will tell you how to come up with the properties that you need to define this hinge, right? So very difficult if I start explaining how to calculate for the moments and then how to calculate for rotations and everything. That one will take a long time, and just for the purpose of this seminar, it will be very difficult for us to show you how to define the hinge and everything, how to calculate the nonlinear properties. But what I can tell you is that you can just simply use basic mechanics to come up with the moment capacities. Some guideline if you want to see a basic force deformation relationship are shown here also. So if you will see, okay. So if you see the curve that is shown over here, there are some guidelines shown in this presentation as to how to come up with the numbers for you to calculate for a hinge, right? So if you can see, we will calculate a yield moment, and then we have ultimate moment that is 1.13 times higher than the yield moment. We have the DL value that will come up from ASE 41. If you want to see, the table is 10-7 in ASE 41 2013. If you want to refer to it, and all of the properties over here are all of the properties that you need to use are there's some typical things that are shown over here. But I cannot go into the detail of how to calculate the moments and rotation. That one will be a bit tricky. But what I can do is that I can show you how to put in the numbers over here and then explain a few things about the hinge. Many different types of options that are available to you for a hinge over here. I will explain these options. I will not go into the mechanics of calculating the moments, right? So some options that you need to understand for a hinge are shown over here. So let me start explaining about the two types of shapes of the relationship that are available. The first shape option over here that you see is called elastic perfectly plastic. Right? Now, what do we mean by elastic perfectly plastic? Elastic perfectly plastic basically means that after the element has yielded, it is perfectly plastic. There is no strain hardening in it. So if you will see, whatever moment that you have for Fu will be the same moment that you have for Fi. So the ultimate and the yield moment capacities will be same. If I use the trilinear option over here, you will see that then the program is allowing you to define some strain hardening. Now, the options, the properties that you will have for the yield moment and for the ultimate moment will not be same. So you are allowed to have a different number. Right? If you see, if I select the elastic perfectly elastic option, you will see, okay, I will do like this. Maybe I just need to start defining a hinge and then start explaining while I'm okay, so now if you will see, if I select the elastic perfectly plastic option, you see that this tab, the tab for the yield moment is closed here. You cannot define the yield moment because now whatever ultimate moment that you define is the same as the yield moment. If I select the option of trilinear, you will see that now I can define separate values for Fu and Fi. Now, if you want to have a behavior, something that is shown in this graph over here, right? You can see that there is a gain in moment. You can use the trilinear option, right? That one was about the different types of shapes that you want to define in the hinge. Right? The other option over here is use of the cross section. Normally we do not use this option, but in the cross section that I defined before, you can also put the moment strength. And then if you select the use cross section option, the moment strength that you define over there in the cross section will come in here. But generally we do not do like that because we already have the tabs available over here, so we just put in the numbers here. So we will not use this option. Symmetry and no symmetry is a bit important to explain. So if you will see, if I select the symmetry options, that means that I only need to input the positive actions over here. The negative actions tab is close to me. If I select the no symmetry options, the negative action tab is available to me now. So I can put in the numbers in here also. What is the difference between positive and negative actions? Basically, the positive and negative actions refer to the positive and the negative moments that you have in a beam. So in a beam, you can have both positive moment capacity and negative moment capacity. Now, if the top and the bottom rebar of the beam are same, you can just use the symmetry options because then you will have the same capacity. If they are not same, you just use the no symmetry options. You calculate the moment capacities for Fy using expected material properties, no phi value, and then you put in the numbers over here. Simple mechanics, nothing fancy to explain. Right? Another tab that is important over here is the tab of strength loss. So if I select this tab, now you will see that the program is allowing me to use the strength loss. Now I can use the strength loss option. So now if I want to define the rotation at which the strength loss will begin, I can define. If I select the no strength loss option, right, I will not be allowed to define the strength loss in the hinge. If I show you the strength loss tab now, since no strength loss option has been selected, there is nothing available to you in this tab over here. So after the ultimate, you just have a constant rotation capacity, right? The moment is sustained. So if I select the strength loss option, you will see that then the strength loss over here is available to me, right? Just some things that I will explain. Okay, I'll explain these things when I import the data in in the hinge, right? Upper bound, lower bound is something that we do not generally use. This one is basically if you want to do your sensitivity analysis, you will need to use upper bound and lower bound. Basically, the sensitivity analysis means that what is the sensitivity of your analysis results based on the properties. So you can define upper bound for the moment properties and lower bound for moment properties, and then the software can use upper bound and lower bound to calculate different results for you. But generally we do not use this, and this one is basically for some research purposes. We do not use this generally also, so this option is always not. Right? And then you have some deformation capacities option. This option, most of the time we will select yes. What do we mean by deformation capacity? What we mean is that if I put some capacity, and I also discussed this yesterday with the limit states thing, if we put some capacity option over here, right? Some capacity, if it is put over here, what the program does is that, okay, we have to imagine that this hinge, all of the hinge that I will, I think this one is not working. Okay, so what we have to imagine is that this hinge, when I define, will actually go to an assembly like this, right? And then this thing is assigned to an element. Now what the program does is that if you put some deformation capacity here, it knows that this hinge will go to that compound, and for this capacity it will give you the DC ratio. Now what you have to remember is that this one is deformation capacity, basically meaning that the capacity that you put over here is deformation, not force. Generally in linear elastic analysis we will never talk about deformation, we will only talk about force DC ratio. So if you want to design a beam, you will design it based on movement strength, you do not design it based on rotation strength. But here, because we always expect this thing to go beyond the moment, so with the capacity that we will put will be the deformation capacity. So generally we use this option. Now if you do not use this option over here, doesn't matter. You can still get the results through some other ways, but this is far easier to do.